Hello everyone. So, in today's lecture we will find the fully developed velocity profile in channel flows. So, we will consider three different cases. One is flow between two parallel plates, then we will consider flow between two parallel plates where one plate is moving with respect to the other, and finally, we will consider flow inside pipe. As you know that to solve the temperature or to solve the energy equation, you need to know the velocity profile. So, if you have a fully developed condition under which if you want to find the velocity profile, so in today's lecture we will find this fully developed velocity profile for different situations. First, we will consider plane Poiseuille flow, which is known as fully developed laminar flow between two infinite parallel plates. You can consider two infinite parallel plates. So, in third direction, as it is infinite, you can consider as a two dimensional flow, and you can have the assumptions of steady, laminar and incompressible flow. Then you can have the assumptions of constant properties where density and viscosity remain constant, and we are anyway considering the fully developed flow. You have already seen that in fully developed flow the velocity v in y direction it is 0. Or first let us consider that you have axial direction as x. Okay. So, this is your x and axial velocity as u, and in y direction you have v velocity and this is your y direction velocity. So, from fully developed velocity profile, so for fully developed flow condition you can write v is equal to 0 everywhere and axial velocity is constant in the axial direction. So, del u by del x will be 0. So, under this assumptions, now let us write the x momentum equation. So, you can see your x momentum equation is rho del u by del t. We are writing for two dimensional situation, u del u by del x plus v del u by del y is equal to minus del p by del x plus mu del 2 u by del x square plus del 2 u by del y square. So, this is your x momentum equation. So, as we have assumed that it is a steady state flow, then obviously del u by del t will be 0. So, this is your 0 as it is steady state. Okay. Del u by del x is 0 fully developed condition, v is 0 fully developed condition, and del 2 u by del x square also 0 as fully developed condition. So, fully developed flow. Okay. So, you can see that as del u by del x is 0, then u is function of y only. Similarly, if you write the y momentum equation, then you will find that only del p by del y is 0. Okay. So, all terms will get cancelled, the temporal term, convection term, the diffusion term. So, all these terms will get cancelled and you will have just all these terms will be 0 and you will have del p by del y is 0. So, you will have from y momentum equation you will get del p by del y is 0. So, that means p is function of x only. So, under this situation this x momentum governing equation you can write as, so u is function of y only. So, you can write d2 u by dy square is equal to 1 by mu dp by dx. Okay. So, because p is function of x only. So, this is your now you got ordinary differential equation. So, we started with the partial differential equation, but invoking the assumptions and putting some terms 0, you got the ordinary differential equation. Now, with proper boundary condition, you will be able to integrate this ordinary differential equation. What are the boundary conditions? So, you can see that we have taken axis in the central line as x and y is measured from the central line from here. So, y and these two parallel plates are separated by a distance 2h. Okay. So, the boundary conditions you can write okay. So, at y is equal to h, your u is 0, as well as at y is equal to minus h, u is equal to 0, because you have no slip boundary condition on upper plate and the bottom plate. So, now let us integrate this equation. So, you have d2u by dy square is equal to 1 by mu dp by dx. Okay. So, if you integrate it, you will get du by dy is equal to 1 by mu dp by dx y plus constant c1, and again if you integrate, then you will get u which is function of y and y square by 2. So, 1 by twice mu dp by dx y square plus c1 y plus c2. So, c1 c2 are integration constant. Now, you invoke the boundary conditions. You have two boundary conditions, because there is, as you have two boundary conditions, you will be able to find the two constants c1 and c2. So, at y is equal to 0, sorry, y is equal to, at y is equal to h, okay, u is 0. So, it is 0. So, you will get 1 by twice mu dp by dx h square plus c1 h plus c2, and similarly at y is equal to minus h, you have u 0. So, 1 by twice mu dp by dx h square minus c1 h plus c2. So, if you say that this is equation number 1 and this is equation number 2, then if you subtract equation 2 from 1, okay, so subtracting equation 2 from equation 1, okay. So, what you will get? So, if you subtract, you will get twice c1 h is equal to 0, that means c1 is 0, okay. And if you add these two equation, adding equations 1 and 2, what you will get? So, this term will get cancelled, this c1 h, this is plus c1 h minus c1 h. So, this will be 0. So, you will get 2 into 1 by twice mu dp by dx h square plus c2 is equal to 0. So, that means you will get c2 is equal to minus 1 by twice mu dp by dx into h square. Okay. So, if you put these values c1 c2, so you will get the final velocity profile. So, velocity profile you will get u y is equal to 1 by twice mu dp by dx y square, c1 is 0 and c2 is minus h square by twice mu dp by dx. So, this you can write u as h square by twice mu minus dp by dx. If you take outside, then you will get 1 minus y square by h square. Okay. So, you can see that it is a parabolic profile. Okay. So, this is parabolic profile for velocity which is symmetric about y is equal to 0. So, you can see the velocity profile here. So, this is your x direction. So, it is actually symmetric about y is equal to 0. So, you will get at y is equal to 0 if you put, then velocity will be maximum, because here you will get maximum velocity which is your center line velocity, and the profile will be parabolic. So, ui is parabolic. Okay. You can see here that we have written this dp by dx as minus dp by dx. So, you can see that flow will takes place from high pressure region to low pressure region. So, in the positive x direction or along the axial direction, your pressure will decrease, hence minus dp by dx will be a positive quantity. That is why we have written as minus dp by dx. So, now we are interested to find what is the mean velocity or average velocity at any cross section. So, you can see that mean or average velocity is physically an equivalent uniform velocity field that could have given rise to the same volume flow rate as that induced by the variable velocity field under consideration. So, if you calculate the volume flow rate q, so you can write q is equal to um into area, okay, where um is the mean velocity, and that if you see, now if you take a small elemental flow area of distance d at a distance y from the center line of distance dy. If you consider an elemental flow area at a distance y from the center line of distance dy, then your this flow area will be just dy into the width of the channel. Width means perpendicular to this board, whatever distance you have. So, that if you consider as width, then you can write w into dy, and total flow area will be, so this is your twice h is the distance between two parallel plates. So, it will be 2h into w. Okay. So, now if you consider this elemental area, so what is flow is happening? So, that you can integrate from minus h to h into u, which is varying along y, into dy into w. Okay. So, that is the elemental area dy into w. So, that we have written. So, now your mean velocity will be 1 by a is your twice h into w, and it will be minus h to h, and what is your velocity profile? Your velocity profile is h square by twice mu minus dp by dx into 1 minus y square by h square into w into dy. Okay. So, this w and w you can cancel. So, now you will get, and this integration minus h to h you can write 0 to h. So, 2 you can take it outside, there will be h square by twice mu is constant, okay, another twice mu will be constant, and minus dp by dx is also constant. So, we will have 0 to h 1 minus y square by h square into dy. So, you can see that we have written this integral minus h to h 0 to h, and these two we have multiplied. So, you can now write this as, so these 2 will get cancelled, okay, 1 h you can write here, and you can write h by twice mu minus dp by dx into, so it will be y minus y cube by 3h square, where limit is 0 to h. So, if you put h, then you are going to get h by twice mu minus dp by dx. Okay. So, h if you put, then it will be h minus h cube by 3 h square. So, this you can see that it will be 2 by 3. So, h by twice mu minus dp by dx. So, it will be twice h by 3. So, hence you can write h square by 3 mu into minus dp by dx. Okay. So, now you can see that you can represent the constant pressure gradient minus dp by dx in terms of the mean velocity. So, you can write minus dp by dx, which is your pressure gradient, as 3 mu into um by h square. Okay. So, you can see here that your right hand side you have mu, which is your fluid property, okay, dynamic viscosity, that is positive quantity, which is your velocity, mean velocity, that is also constant and positive, and h, which is your the distance from the central line, so that is also constant. So, obviously right hand side is constant, that means minus dp by dx is constant. So, now if you find the velocity profile, so you can write in terms of mean velocity u, which is function of y, that is your h square by twice mu minus dp by dx into 1 minus y square by h square. So, now this minus dp by dx, if you put it here, you are going to get 3 by 2 um into 1 minus y square by h square. Okay. So, your velocity profile you can write in terms of mean velocity as 3 by 2 1 minus y square minus h square. Okay. And if you find the maximum velocity, then you have to find the velocity at central line, which is y is equal to 0. So, you will get maximum velocity will occur at central line, okay, where u at y is equal to 0. So, if you put it, you are going to get h square by twice mu minus dp by dx, and that if you write minus dp by dx in terms of 3 mu by h square, then you are going to get you are going to get h square. So, uc will be h square by twice mu, and minus dp by dx is 3 mu divided by h square. So, it will be just 3 by 2 So, you can see that in case of flow, fully developed flow inside two infinite parallel plates, your maximum velocity is 1.5 times the average velocity, okay, because here you can see that uc, which is your maximum velocity, is 1.5 times the mean velocity for fully developed flow. Now, if you find what is the shear stress acting on the wall, then you can write shear stress, okay. So, that you can write tau w as mu du by dy, okay. So, at any wall you can calculate. So, y is equal to h, let us calculate. So, you can write mu into du by dy. So, what is du by dy? So, you can see this is you will get 1 by mu dp by dx into h, okay, at y is equal to h. So, you will get h into dp by dx, okay, and dp by dx minus dp by dx, you know, minus dp by dx is 3 mu by h. So, if you put it, then tau w at y is equal to h, you will get h into minus 3 mu by h, okay. So, you are going to get minus 3 mu So, similarly, if you calculate tau w at y is equal to minus h, okay. So, you can see it will be 3 mu into and you can see that your shear stress inside the fluid, it will vary linearly. Now, we will define the friction factor. Okay. So, this is the non-dimensional representation of the pressure gradient. So, if you calculate non-dimensional pressure drop relation, then that is known as the friction factor. So, friction factor you can calculate. Okay. So, this is minus dP by dx, okay, into the channel height divided by, so this is non-dimensionalization with half rho um square. Okay. So, this if you find, so what you are going to get? So, minus dP by dx is this one. So, you can write 3 mu um by h into 2h divided by half into rho um square. Okay. So, if you rearrange, you will get this as 24, okay, 2 to 4 into 3 12, 12 into 2 we are writing, because we will write this rho um into 2h, okay, divided by mu. So, you can see this is your Reynolds number based on the mean velocity and the channel height, then you can write 24 by REH. So, friction factor we have represented in the terms of the non-dimensional number, Reynolds number based on the channel height. Okay. So, friction factor F is equal to 24 by REH. If you calculate the skin friction coefficient, okay. So, this is dimensionless representation of the wall shear stress. So, skin friction coefficient, so it is represented as CF. Okay. So, this is your modulus of tau w divided by half rho um square. So, this is just dimensionless representation of the wall shear stress. So, you can see this is your 3 mu um divided by half into rho um square. So, you can rearrange it and you will get 12 by rho um into 2h divided by mu, and you can write 12 by REH. Okay. So, for the fully developed flow inside two parallel plates, we have calculated the shear stress on the wall, and hence we have calculated the skin friction factor, which is your dimensionless representation of the wall shear stress as 12 by REH, where RE2H is the Reynolds number based on the channel height. Okay. So, this is your Reynolds number. So, it is 2H, sorry. So, this is your based on 2H. So, Reynolds number we have defined based on mean velocity um and the channel height 2H. Next, we will consider plane Courtet flow. This is the flow between two infinite parallel plates, where one plate is moving with respect to the other. So, you can see that these are the two fixed plates, okay, and this upper plate is moving with velocity u in the axial direction. Okay. So, some constant velocity u it is moving with respect to the bottom wall. So, this is your x direction and y is measured from the bottom wall, and bottom wall is stationary. Okay. So, bottom wall is stationary and upper wall is moving, okay, with constant velocity u, and y is measured from the bottom wall, and the distance between two parallel plates is h. Okay. So, in this scenario, now you can see that the flow is taking place. So, here you can see that the flow is taking place due to the shear. Okay. So, the upper plate is moving. So, due to the shear, there will be a velocity inside the channel. So, this is known as shear driven flow, where your pressure gradient is absent in this particular case. That is why we have told as plane Courtet flow. Okay. So, where you have the external pressure gradient as well, along with the shear driven flow, then it will be Courte flow, but here we are considering plain Courte flow, where we are assuming that pressure gradient is 0. So, in this particular case, now we are considering minus dP by dx as 0, okay, and fully developed condition. So, obviously your governing equation whatever we have derived in earlier case, you can write d2u by dy square is equal to 0, because we have considered fully developed flow. So, your y direction velocity v is 0 as well as your del u by del x will be 0, because there will be no change in the axial velocity in the axial direction. So, your governing equation is del 2 u by del y square is equal to 0, and what are the boundary conditions? Boundary conditions are at y is equal to 0, bottom wall u is 0, and upper wall at y is equal to h, it is moving with velocity capital U. So, you integrate this equation. So, you will get du by dy is c1, and u which is function of y, you can write c1 y plus c2. So, c1 and c2 are constants. So, you can see that you will get a linear velocity profile. Okay. So, now invoke the boundary conditions at y is equal to 0, u is 0. Okay. So, u is 0. So, you will get c2 is 0, and at y is equal to h, u is 0. So, you will get c1 sorry at y is equal to h, you will get u is equal to u. So, you will get c1 into h, c2 is 0. So, obviously c1 is u by h. So, hence you will get the velocity profile u which is function of y as u into y by h. Okay. And you can see that y is equal to 0, it is 0 velocity, at y is equal to h it is capital U, and it is linearly varying. Okay. It is linearly varying, because from the velocity profile you can see that it is a velocity varies linearly across the gap. Okay. And if you calculate the shear stress on wall, so you can see that du by dy will be a constant, because here you can see tau w, okay, will be du by dy, and du by dy is constant c1. So, that is u by h. So, in both the plates you can find that your wall shear stress will be u by h. So, along inside the flow also the shear stress will be constant. So, now if you calculate the skin friction coefficient, and what will be your mean velocity? So, if you calculate the mean velocity, so it is is 1 by h 0 to h. So, at a distance y you are taking one elemental flow area, that is dy. So, it will be u into dy, and what is u? U is your u into y by h into dy. So, it will be y square by 2, hence will be just u by 2, okay, u by 2. If you calculate the skin friction coefficient, so you will find for this particular case Cf is equal to tau w by half rho um square. Okay. So, tau w is just mu u by h, okay, mu u by h divided by half into rho, and is u square by 2. So, u square by 4, u square by 4. So, if you rearrange you will get 8 by rho u h divided by mu. So, you will get 8 by REH. So, we are writing this Reynolds number based on your upper velocity, okay, upper plate velocity u. So, that will be REH is equal to rho u h by mu. So, now we will consider fully developed flow inside pipe. So, this flow is known as Hazen-Poiseuille flow. So, you can see this is your axial direction x, okay, and radial direction is r, and we are considering axisymmetric flow. That means that in circumferential direction, in phi direction, there will be no variation of any variable. Okay. So, that is your axisymmetric. So, in case of axisymmetric, your u will be function of r only, and as it is fully developed condition, then the axial velocity u will be constant, or u is function of r only, it is not function of x. Okay. So, del u by del x will be 0. So, if you consider that, so you can see that it is a pipe, okay, and these are your pipe wall, and the pipe radius is r naught, and this is your central line, and r is measured from the center. So, if you write the fully developed condition, so in this particular case x is your axial direction, okay, r is your radial direction, u is your axial velocity, and v is your radial velocity. Okay. So, as it is a fully developed flow, okay, so del u by del x will be 0, because your in axial direction there will be no change in the velocity profile. So, del u by del x will be 0. So, u is function of r only, okay, and radial velocity everywhere v will be 0, and one most important assumptions that we have taken, it is axis symmetric flow. Okay. So, if you consider that your circumferential direction, okay, if you measure, so let us say this is your phi or theta, okay, let us say phi, then del of del phi of any variable is 0, and the velocity in phi direction also 0. Okay. So, if you say that velocity w which is in phi direction, so it will be 0 in axisymmetric flow. Okay. So, if you consider the momentum equation, then you can see that you are invoking all these assumptions, okay, you will get this ordinary differential equation, which is your governing equation. Okay. You will get left hand side all will be 0, you have a axial pressure variation del p by del x, and you will get mu 1 by r del of del r, r into del u by del r. Okay. Here also you will find that p is function of x only, and you can write del p by del x as dp by dx, and u is function of r only. So, you can write d of dr, r into du by dr is equal to 1 by mu, or 1 by mu dp by dx into r. Okay. So, now if you integrate it, so you will get r du by dr is equal to 1 by twice mu dp by dx into r square plus C1. If you divide by r, then du by dr will be 1 by twice mu dp by dx into r plus C1 by r, and again if you integrate, then you will get the velocity profile as 1 by 4 mu dp by dx r square plus C1 ln r plus C2. So, now you invoke the boundary condition. What are the boundary conditions? At r is equal to 0, you have u finite, and at r is equal to r naught, which is your wall, you have velocity 0, u is 0. So, if you write boundary conditions, okay. So, at r is equal to 0, u is 0, sorry, u is finite. At r is equal to 0, u is finite. So, you can see that if u is finite, then C1 must be 0. Okay. So, C1 is 0, and at r is equal to r naught, u is 0, because that is your wall. So, it will be r naught. So, you will get 0 is equal to r naught square by 4 mu dp by dx plus C2. So, C2 is minus r naught square by 4 mu dp by dx. Okay. Hence, you can write the velocity profile as, so velocity profile you can write now. Okay. U is function of r only, and if you put the constant, so you can see that C2 is minus r naught square by 4 mu dp by dx. So, you can write as 1 by 4 mu dp by dx, 1 by 4 mu dp by dx r square minus 1 by 4 mu dp by dx r naught square. Okay. So, hence you will get u r as 1 by 4 mu r naught square minus dp by dx. So, minus dp by dx, because minus dp by dx is positive. Okay. So, this into, so minus I have taken outside, so it will be 1 minus r square by r naught square. Okay. So, you can see that this is also your parabolic profile. Okay. So, you can see you will get a parabolic velocity profile where r is equal to 0, you will get the maximum velocity, and at walls obviously it is 0. So, r is equal to 0, r is equal to r naught, it is 0. So, you will get a velocity profile which is u is function of r. Okay. So, and you will get a parabolic profile, and we are writing u as minus dp by dx in term, we are writing u r in terms of minus dp by dx, because minus dp by dx is positive quantity, because in axial direction you have minus dp by dx is positive, because your pressure gradient is decreasing in the axial direction. So, generally if dp by dx, okay, is less than 0, so this is known as favorable pressure gradient, and if dp by dx is greater than 0, then it is known as adverse pressure gradient, because you have pressure gradient as positive and your flow reversal may take place. So, generally dp by dx, okay, is less than 0, then it is known as favorable pressure gradient, favorable pressure gradient, and if dp by dx is greater than 0, then it is a adverse pressure gradient. Now, you want to calculate the mean velocity in Hazen-Poiseuille flow. So, you can calculate the mean velocity as, so q, which is your volume flow rate, you can write um into A is equal to integral over the area, flow area, into u, which is function of r into dA. So, in this particular case you can see that you have a circular cross section. So, at a distance r you take one elemental flow area. So, this is your elemental flow area, okay, of distance dr. So, what will be your dA in this particular case? So, this is the elemental flow area. So, dA will be twice pi r, okay. So, this is the perimeter into the distance dr. So, this is the area, and total area is A is equal to pi r naught square, okay. So, if you put it here, so you will get um as 1 by area. So, this is your 1 by pi r naught square. Now, you are varying 0 to r naught. What is your ur? Ur is r naught square by 4 mu minus dp by dx, okay, into 1 minus r square by r naught square, and what is dA? dA is twice pi r dr. So, this will be twice pi r dr. Okay. So, this pi you cancel, okay, and you can write it as, so this other r naught square also you can cancel because this is constant. So, you can write as, so this is 4 mu, this is your 2. So, it will be 1 by twice mu minus dp by dx, okay, integral over 0 to r naught, r this you multiply here. So, it will be r minus r cube by r naught square into dr. So, if you integrate it, so you will get 1 by twice mu minus dp by dx. So, you will get this as r square by 2 minus r to the power 4 by 4 r naught square 0 to r naught. So, if you put the values, so it will be r naught square by 2, it will be r naught square by 4. So, it will be 1 by 4. So, you will get 1 by twice mu minus dp by dx into r naught square by 4. So, hence you will get as r naught square by 8 mu minus dp by dx. So, now you can express minus dp by dx in terms of mean velocity. So, minus dp by dx you can express in terms of mean velocity. So, that will be 8 mu by r naught square into Okay. So, now you can express this velocity profile in terms of the mean velocity. So, you can see that u, which is function of r, if you minus dp by dx, if you invoke there, you will get twice into 1 minus r square by r naught square. Okay. Similarly, now if you find the maximum velocity which will occur at the central line where r is equal to 0, then you can write maximum velocity okay, u max, which is your central line velocity, u c is equal to u at r is equal to 0. Okay. So, if you put it here, you can see that it will be just twice Okay. So, in this particular case, you can see that when you consider the flow inside pipe, then your maximum velocity will be twice of the average velocity or mean velocity. Okay. So, this your u max, you can see it is twice into the mean velocity, and when we consider flow between two parallel plates, u max was 1.5 times the mean velocity So, you should remember here. So, when you consider pipe flow, your maximum velocity is twice the mean velocity, and when you consider flow between parallel plates, then your maximum velocity will be 1.5 times the average velocity. So, now we want to calculate the shear stress at the wall, that means at r is equal to r naught, we want to calculate the shear stress. So, tau w you can write as mu du by dr at r is equal to r naught. So, shear stress you can calculate tau w as mu into du by dr at r is equal to r naught. Okay. So, you can see tau w you can write mu into du by dr, you can represent as 1 by twice mu minus dp by dx into r naught. Okay. So, it will be just r naught by 2 minus dp by dx, and what is minus dp by dx is 8 mu r naught square by So, you will see that if you put it, you will get 8 mu by twice r naught. Okay. So, now if you want to calculate the skin friction coefficient, so skin friction coefficient. Okay, what is skin friction coefficient? It is the dimensionless shear stress, okay, or sometimes it is known as fanning friction coefficient. Fanning friction coefficient. Okay, so you can write Cf as mod tau w divided by half rho square. Okay, so you can see that tau w is this. So, 8 mu u m by twice r naught into half into rho u m square. So, if you rearrange it, you can write it as 16 by rho u m twice r naught divided by mu. So, you can write 16 by r e d. D is the diameter of the pipe. So, that is twice r naught. So, Reynolds number we have defined here, Reynolds number we have defined here based on the diameter, okay, and mean velocity. So, rho u m twice r naught divided by mu. Similarly, if you want to calculate the friction factor, which is your non-dimensional pressure gradient, so that you can write it as friction factor, okay. For this particular case, it is known as Darcy friction factor also, okay. So, you can see that F will be minus dP by dx, okay, into the channel diameter twice r naught divided by half rho u m square, okay. So, minus dP by dx is this one. So, 8 mu u m by r naught square, okay, into twice r naught and divided by half rho u m square. So, if you rearrange it, okay, so you will get 64 divided by rho u m into twice r naught divided by mu. So, you will get 64 by r e d. Okay. So, your friction factor is 64 by r e d. So, if you see that your friction factor is 4 times your skin friction coefficient, okay. Friction factor. So, this is your 16 into 4 and 16 by r e d is your C f. So, f is 4 into C f. So, in today's lecture we have found the fully developed velocity profile for 3 different cases. First case we considered as flow between 2 infinite parallel plates, where your v velocity is 0 and del u by del x is 0, which is your axial velocity does not change in the x direction. So, with that condition we found the velocity profile and we have found that it is parabolic in nature, and then we calculated the mean velocity and then we calculated the skin friction coefficient as well as the friction factor. Next we considered the plane Courte flow, where we consider the shear driven flow between 2 parallel plates, where bottom plate is stationary and upper plate is moving with velocity u in the positive x direction. And we have seen that velocity varies linearly from bottom plate to top plate. Next we considered the Hazen-Poiseuille flow. This is the fully developed flow inside pipe. Here we found the velocity profile u as function of r, and that is also parabolic in nature. In this particular case also we found the mean velocity, then skin friction coefficient and friction factor, and we have found that friction factor is 4 times the skin friction coefficient. In Hazen-Poiseuille flow we have seen that your maximum velocity is 2 times the average velocity, and in case of plane Poiseuille flow your maximum velocity is 1.5 times the average velocity. In fully developed case we have found the velocity profile in different channels and we have found the mean velocity. These we will use in the next module when we will find the temperature distribution inside this channel flow. Thank you.